All right. If you guys can turn to page 11. My God. Okay, guys. So your quiz is on Thursday over area volume. We'll spend the first half of class talking about this particular type of FRQ, which will be what your quiz will look like the Wednesday after you get back from break. But we use the second half of class to continue doing quiz review for Thursday's area volume quiz. So again, just to go over the calendar again. So quiz Thursday. After on Friday, we're going to continue looking at what we're going to do today with table of values. And then we'll spend some time Monday and Tuesday after break, but I'll also want to start reviewing Riemann sums and differential equations, which will be your second FRQ quiz. So so there'll be a quiz coming up Wednesday after break, and then Tuesday after that, and then Friday, that second to last week will be partner quiz. And each of these quiz grades will be buffered by your homework grades. And so it's important that you try to keep up with your homework. The homework for, there's going to be 3 review packets. Packet 1 will go towards half of your quiz grade. Packet 2 will be half of your second quiz grade. Packet 3 will be half of your partner quiz grade. Okay. All right, so let's take a look at 11, 12. I like, so this is a type of FRQ that we've seen in the past. And the reason that I like this being the first quiz is because this goes over a lot of AP topics, all condensed into one STEM problem. So your quiz will be like this, where you're going to be given a table of values. You have basically a derivative graph, and then you have multiple parts across 2 pages. So your quiz will be of this length. It'll be just 2 pages, and then I'll just we'll get through this packet probably before break, and then I'll give you some more additional review worksheets leading up to Wednesday quiz. So you'll get more comfortable with the types of questions that you're going to see on this on the quiz. Right. So, oh, and also if you're working ahead of me, that's fine. There's a key on page 13, 14. So you can see you can check your progress there as well. All right. So let f and f prime be a differentiable function. Table of values gives the table gives values of f and its derivative f prime. So we have f and f prime, and then we have selected values of x. G of x is defined as a function. H of x is the integral from 6 to x of j of t dt. We'll talk about that. And then we have a graph of j of x. So part A, is there a value between 1 and 5 such that f double prime of c is equal to -3/4? So if you look, we don't have a table for f double prime, but we do have a table for f prime. And anytime we're trying to guarantee a slope of some value, we should be considering, okay, they're trying to get us to use MBT. So even though MBT typically is this formula, f prime of c equals f of b minus f of a over b minus a, right? It's the average rate of change equaling the instantaneous rate of change. We can also adapt this formula for NBT for this problem, if I want to guarantee a slope of f prime, I can just find the rate of change of f prime. Right? So I can adapt this formula and just make everything go down one derivative. So I can use this as my setup. If I can show that the slope between f prime of b and f prime of a is equal to -3/4, then there must be a place where f double prime of c is exactly -3/4. Right? So let's see if we can get this to be proven true. It's telling us between 1 and 5, so they're giving us those endpoints. So let's see if we can show that the slope between the two endpoints of my f prime table is going to produce this value. Okay, if it does, then we can go through a mean value theorem. We can guarantee that value because we have a differentiable function. So we know we have continuity and we have differentiability for our f prime. Okay, so let's test it out. Let's do f prime of 5 minus f prime of 1 over 5 minus 1. So f prime of 5 is -2. F prime of 1 is 1. So we get -3/4, which is exactly the value that we're trying to target. So if we can draw a slope between the two endpoints on the f prime graph, that's -3/4, there must be a slope. The graph must experience -3/4 somewhere along that path. Right? If my average slope is -3/4, we must have this exact value. Okay. So we can say by mean value theorem, then, since f prime is continuous on the closed interval and differentiable on the open interval, there must be a value where f double prime c is equal to -3/4. So we're just applying mean value theorem.
On the exam, can you write the abbreviation, or do you have to write out mean value?
That's fine. Abbreviation is fine. Yeah, on the AP exam as well. Actually, on the AP exam, they may not even care that you mentioned mean value theorem. They're looking for the fact that that your conditions, if you can state your conditions and if you can show your work, then we don't have to name it, but I think it's good to just name it just in case. So again, continuous is with brackets, differentiable is with print. If I happen to be going too fast, just know that you have a key on the next page as well. Okay, part B. Let k of x be defined as f of j of x. Write an equation for the tangent line to the graph of k at x equals 2. So we're just trying to get our tangent line equation. So we're going to plug 2 in to get our order pair. And then we can build the derivative and then plug 2 in to get the slope and then point slope 1. So let's find the order pair first. So we have information spread across table and graph here. So let's start off with j of 2. So this is a composite function here. So j of 2 is down here at -1. And then f of -1 is equal to 4. Okay, so we have order pair out of the way. K of 2 equals 4. We can use that later. Next up, we have to find the slope. To find the slope, we got to get to the derivative. So we should recognize this as what? If I want to find the derivative of K prime, I got to go through what? Chain rule. Yeah. So if you recall, the derivative for chain rule, you don't have to write this down. So I want to show you what the rule is. F prime of g of x times g prime. Right. So the rule for chain rule is we take the outside derivative, whatever the outside function is, build that derivative, keep the inside the same, and then multiply by the inside derivative. So in this case, if I want to find the derivative of k prime of x, it'll be f prime of j of x times j prime. So k prime of x is equal to f prime of j of x times j prime. Okay, replace all your x values with 2. And then start piecing information into the derivative. We start off with j of 2. J of 2 is equal to -1. So now all we're left to find is f prime of -1 and j prime of 2. F prime of -1, we can pull from the table. -3. And then j prime of 2, here's my j graph. So j prime of 2 is asking for the what? The slope. Yeah, so just pick any 2 points and do rise over 1. We'll get down 2 over 1, so slope is going to be -2 along this line segment. So we have our order pair, we have our slope. We can now build our point slope form. You don't have to write the definition out. I just want to show. Okay, any questions here? Building. Just be careful with chain rule that you're building it piece by piece, gathering information from the inside out, and then eventually getting to your slope. Part C, we're finding a slope of a tangent line to the graph at x equals pi, graph of v. So now we're also finding the derivative at a point, but now it's involving this g of x function. And now we're going to actually be using our derivative rules to build our g prime and then plugging in pi. So if you recall the rules, sine of u is cosine of u times u prime, and then e to the u's rule is e to the u times u prime. After you find the derivative, we can plug pi in to get the slope. Right. What's cosine of 2x's derivative? Yeah, negative sine 2x times 2. So all that's going to have to go down here. I put the 2 out in front. You don't. That's where it's going to eventually end up. I'm going to say negative cosine, negative sine of 2x. Sine of u becomes cosine of u times u prime. E to the u becomes e to the u times u prime. U prime is asking for my entire exponent's derivative. So cosine of 2x becomes negative sine of 2x times 2. Okay, so now that we have our derivative, replace every x with pi. Okay, cosine of 3 pi is anything as cosine of pi. So that's just going to be cosine of pi is negative 1. And then cosine of 2 pi, that's going to be 1, right? Cosine of 0 is 1, so minus e to the first power. But then sine of 2 pi is 0. And 0 times anything is 0. So that's going to wipe out my entire second term. The only thing left over is negative 3. Okay. Any questions so far? Part D, find h of 4 and h prime of 4. So h of 4 is simply involving the region between the graph and the x-axis of my j of t function. And h prime, I can use second theorem to build that, right? So let's do h of 4 first. So h of 4, I'm just using my definition that's provided for me. It's forcing me to put a 4 up there because that's where my variable is. But because I want to read the graph, I prefer to have the bounds in order, right? Lower bound to upper bound. So what can I do? Yeah, flip it, make it a negative. And now we can just read directly from left to right, and then whatever we get, we can just make it a negative at the end. So let's look at our graph here. Remember our graph, we only look at the region between the graph and the x-axis. So we're only caring about what we see in these regions. A bunch of triangles there. So we know area is going to be 1/2 base times height. And also we know that displacement causes regions below the x-axis to be negative. So we're just looking at between 4 and 6. So 4 and 6 is just this triangle here. 1/2 base times height. That's going to be a value of 3. So we can just make it a 3, but then there's a negative in front, so negative 3. Next part, find h prime of 4. Before I can find h prime of 4, I want to first find h prime of x. So h prime of x requires me to take the derivative of this integral. And this should remind us of second theorem. We know second theorem are going to cancel these two operations out. You can just plug that upper bound in for a t and multiply it by x's derivative, which is times 1. So that's not going to change anything. So h prime of x is simply j of x. So if I want to find h prime of 4, simply the order pair on my j graph. So what's j of 4 equal to? 0. Yeah, that's just the x-intercept there. J of 4 is just going to be 0. Okay, next page. Part E, on what interval is h increasing and concave down? I meant for this to be at the same time. So we learned from the previous page that h prime is equal to j of x, right? We know that h prime is equal to j. So we know that this is basically the derivative graph of h. So we can just label accordingly, understanding that this is our derivative graph. Anything above is positive slope, anything below is negative slope. We know the peaks and valleys or will end up being points of inflection. We know positive is concave up, negative is concave down. So let's create our slope and concavity sign line based off of our h prime graph. X-intercepts will be where your critical points. So it's going to be at 1.5 and 4. What's the slope behavior between 0 to 1.5? Above, yeah, above the x-axis, so positive slope. Between 1.5 and 4, below, it's negative. And then to the right, between 4 and 6, above, yeah. If I want to create my f double prime sign line, now I want to pull concavity information, again, from 0 to 6. Now we know points of inflection is going to be peaks and valleys, right? So 1, 3, and 5. Trying to line everything up so it's easy for me to compare. Now we look at slope, right? Because we know the second derivative is describing the slope behavior of my derivative of my j of x. So what do you see here? Initially, this is what? Positive slope. So positive slope is going to translate to concave up. Negative slope is going to translate to concave down. And it's going to keep alternating, right? Positive slope, negative slope. Okay, so we're looking for interval where the graph is going to be increasing and concave down. So basically, you can also look at this graph and tell, okay, I'm looking for something that is above the x-axis, but showing me a negative slope. So increasing and concave down. So it's going to be in this region here. And then this region. Increasing and concave down at the same time. Increasing and concave down at the same time. Okay, next up, find the absolute max, absolute min. What does this remind us of? We're gonna involve what? Yeah, EVT, extreme value theorem. So that means we want to test endpoints and critical points. And if you want to pick out endpoints, critical points, just make sure that you're pulling them from H prime. We don't care about H double prime. This is not going to give us any points that we need. So we're only going to be worried about 0, 1.5, 4, and 6 because we have 2 endpoints and we have 2 relative max or 2 relative extremes. And they're all going to get inserted into H of X, which is going to require us to involve areas and displacements under our J graph. So I'm going to go ahead and just find all the areas that I need so that I can just have easy access to them. So I already know that this is going to be 3. This here, 1/2 base times height. My width here is 2.5, so it's going to be 1/2 times 2.5 times -3, which is -3.75. Okay, and you will get to use your calculators on all the quizzes. Right. 1/2 base times height here. So 1/2 times 1.5 times 1. So give me 0.75. So this small triangle is 0.75. This is -3.75, and this is +3. So extreme value theorem, again, we're going to test the points from our H prime sign line. So we know here's the formula that we're going to use. Okay, sorry, J of T. So let's start with 0. So because we want to read the graph from left to right, I always prefer to adjust the bounds so that I can read exactly what I see. So my bounds are out of order, so I'm going to change my bounds, but then make sure I adjust with the change in sign as well. So from 0 to 6, I can just add up all these values there, 0.75 minus 3.5 plus 3. With a negative in front. Now this does add up to be 0, so that change in sign is not going to matter. Next up, let's test 1.5. Again, the bounds are out of order, so pull a negative in front. So from 1.5 to 6, it'll be these two triangles, -3.75 plus 3. Ends up being a positive 0.75. We have 2 candidates. Let's do 2 more. H of 4. Again, out of order. Pull a negative in front. So from 4 to 6, it's just that final triangle, which is a +3. But I'm keeping track of the fact that I changed my sign there, so -3. And what's nice about H of 6? 0, because yeah, my bounds are the same, so it's just 0 going to 0 out. So my candidates, we're just looking at these values to pick out the highest. Highest will be your max, lowest will be your min. So we can say absolute max is 0.75. Absolute min is -3. Okay, I only want the y values. Don't give me order pairs. Don't give me the x value. Okay, next part, evaluate the integral of f double prime. So we're going to use this this rule that we know, basically the first theorem. The first theorem says that if I have the integral from a to b of f double prime of x, that's going to be the same thing as my f double prime. This is going to rise up to f prime, so it's going to be f prime of b minus f prime of a. Okay, so this is just a rearranging or an adapted version of first theorem. First theorem just says, okay, I can just take whatever my integrand is, make it go through the antiderivative process, whatever that process is. In this case, f double prime will rise up to f prime, and then plug in my upper bound minus lower bound. However, there's something inside of that parenthesis, so we do have to go through a little bit of use substitution in order to adjust for the fact that there's something inside the parentheses. So we'll go through use substitution first, and then we can put into this formula. So our u value is 2x. Our derivative is 2. Solve for dx, u over 2. I'm trying to get everything to be in terms of u. There is a leftover 1/2, so we need to pull that 1/2 out in front. So now that we have everything that is clean in terms of one variable, in terms of u, we can evaluate the integral. We know second derivative will rise up to f prime. The 1/2 will come along with it. So 1/2 f prime of u minus 1/2 f prime of u. So here's my antiderivative. I want to bring back my original variable. I'm sorry. I'm trying to do too many things here at once. So I haven't done the bounds yet. My bad. So we know f double prime will just rise up to f prime, right? We know f double prime is just f prime, but then let's worry about the bounds a little bit later. Let's replace the u back in terms of x. Right, and now let's do half bracket, and then we can worry about plugging in our upper and lower bounds. Now that my variables are both in terms of x. Okay, so upper bound first. Minus the lower bound. And then we can use our table of values to try to get it down to something that is numeric. So f prime of 6, you look at your table, f prime of 6 equals 2. And then f prime of 2 is 3. Right, so this is basically what your quiz will feature. There will be chain rule component. There will be a part where you're doing use substitution. There's be a part where you got to involve interpreting a derivative graph, extreme value theorem. So we're just going to cycle through different variations of this. Today, Friday, and then Monday and Tuesday after break. Okay, let's continue. We have a little bit of time here. So let's go to page 15. Or sorry, 16. This is more table. This is more Riemann sums, but this is good too since we're gonna have to do a Riemann sums for our FRQ quiz that's coming up. Not this next one, but the one after. Okay, so a sand pit is being filled with sand whose height at any time t is given by a differentiable function h of t. So we know it's a smooth curve all the way through. Let h prime be a differentiable function representing the rate at which the height of the sand pit grows in inches per minute. It is known that h prime is increasing over its entire domain. So the rate at which sand is being added to the sand pit is 1 inch per minute, and then goes 2 inches per minute, then 5 and 7 and 10. So the rate keeps growing. We have an increasing rate over the course of this interval. Okay, values of h prime are given. The height of the sand pit is 40 inches to begin with at, 40 inches at 9 minutes. So so up until, there's, so obviously it's going to start off lower than 40 inches, but by the time it gets up to 9 minutes, it's going to be up to 40 inches after all the increasing rate. Estimate h double prime of 2. So h double prime of 2, we know that's involving the slope of h prime. So we can just pick the two closest order pairs and just find the slope. And we know it's going to be an estimation since we're just relying on the closest information sets of order pairs to find that rate of change. So change in y over change in x, or change in h prime over the change in t. And then what's our unit of measure going to be? H prime is already inches per minute, so this will be what? Inches per minute squared. So the way that we want to interpret is we don't want to say rate of a rate. We don't want to say acceleration. That doesn't fit the context. We want to say something in the terms of, how that rate change. Is the rate increasing or the rate decreasing? In this case, the rate is going to be increasing, right? So you can see that 1 to 2 to 5 to 7, there's an increasing rate, right? So rate of sand pit is increasing at 3.5 inches per minute squared at t equals 2 minutes. So we want to be able to use these words here involving something involving rate is increasing or rate is decreasing. That will indicate that second derivative relationship. Part B, use Riemann sum with subintervals given in the table. So that means we want to use every subinterval that we see. So you can go ahead and build your subintervals, subtract your t-values to get your width, and then pick out the appropriate h prime to get your height. So we're going to do 1 times 2, 2 times 5, 6 times 7, and 3 times 10. Now we know that h prime is at the level of inches per minute. So we know the integral is going to take it up to inches. So what that indicates to us, that 84 inches that we're going to get is indicating the change in height in that 12 minutes, right? You keep adding inches per minute. So it's going to be at some heights at 0 minutes, but after 12 minutes, that sand pile or that sand pit is going to grow 84 inches or add 84 inches in height in that 12-minute period. Okay, so we got through most of the work I'm going to be checking on Friday. It says page 11 through 17, but a lot of these are just keys that we skipped over. So we did page 11 and 12. You just have to finish 16 and 17, and I'll be checking that on Friday. So again, when you're showing me your work on time, you're earning the full amount of points that you can get for your quiz, and your quiz, your homework, this packet homework is going to be, classwork homework is going to count 50% of your quiz grade. Thank you.
Because I know in this.
Yeah, so I thought page 1 and 2. Okay, you were here.
Okay, if I saw. I know it's like. Yeah. I know that. Oh my God.
That's all I. That's all. Okay, thanks. Me on Friday. Bye. I'll be. So I'm not. You want to be counted present. Yes, I do. All right, thank you.
Wait, what?
Or for senior service.
It's just a study hall, so you can spend the time studying for your quiz or yeah. Anyway. There's it's just gonna be pages 11 through 17. I'll check it out. Yeah, thank you. Good day.
So this Thursday I won't be here. I have an internship trip,
Oh, okay.
so.
Do you want to take the quiz on Friday? Okay. You can take it in class or you can take it, another time.
I'll take a class.
Okay, that sounds good. All right, see you then.
You too.